we started our discussion on Laplace transform, right? So before I continue our discussion, I would give you some details about the exam, right? So according to our schedule, you are going to have the exam on tomorrow. I would upload the exam on tomorrow, and I would allow you 2 or 3 days to finish that and submit. Okay, so
Are they gonna be on paper or?
yeah, on paper. So this is my plan. Uh, there would be 6 problems, including extra credit problems, right? 6 problems, including extra credit problem. And first problem would be from some applications. First 2 problems are applications. First 2 problems. So get familiarized with RC circuit, those formulas, right? You can use your books when you're writing the exam, right? It's not a closed book exam, right? You can use your books, internet, anything, right?
Notes.
Yeah, you can use anything. You can use books, your notes, internet, anything, right? Circuit and mixing problem and Newton's Coulomb laws, right? Then I would test you on integration factor method. Sometimes for these problems also you would need integration factor method, right? Because in applications also we are deriving an ODE, then we have to solve that, right? When you are solving those problems, you have to use one of those techniques, right? So I would test you on integration factor method. Right. And exact differential equations. Exact differential equations, and we discussed about 2 substitutions, Bernoulli's substitution and that y equals ux substitution. I would test one of them. Right. Substitutions. Okay, so 2 applications problems and 2 problems from these things, and uh, 1 problem from Laplace transform. It would be not a very difficult problem, right? So most probably it would be from the ideas that we discussed on Friday. Right. Sometimes when you're solving that problem, the things that I'm going to discuss on today also might be important, right? So 5 problems, and I would give another problem for extra credit. So altogether you have 6 problems. Okay. Right. So any questions that you need to know about? I would not give very trivial problems, right? Then you can go to the internet and get the answer, right? So problems might be difficult, but give a try. Because now ChatGPT is there, so you can just, if I give very trivial problem, then it's easy, right? So, but I need you to try, right? And I need you to think. That's what I need, right? Right. So let's continue our discussion on Laplace transform. Any questions that you need to clarify about the exam?
Was cool. Mentioning any thought.
Newton's mixing problem is something like you have a tank and you have an inlet and outlet. That kind of problem. These two are the most important. mentioned. We were discussing about the exam. Those are the ideas.
Have class. You still have class, like, tomorrow? Well,
Yeah, yeah, we are going to have a class. I think you have enough time. 2 or 3 days means you can do those problems within those days. Right. Yeah, I would most probably 3 days. Right. Because we are having homework also. So then you have enough time. And when you are submitting your answers, uh, write the answers very clearly, right? Because this is a take-home exam. Try to attach your, suppose you did first problem at first, then third problem, then fifth problem like that. But when you're attaching the answer, try to attach them in order. 1, 2, 3, 4, 5. And when you're scanning your answers, scan them very clearly, right? And name the file by your R number or your name. Name would be okay. Your last name, right? So, and don't attach images. Convert it to PDF and submit. Okay. And try to elaborate your answers. Try to explain everything, right? Don't write short answers, right? Because you do not have any time constraints, right? So think this as a project, right? So write your answers very clearly and try to explain everything. Then that would be good for you, right? Explain every step very clearly, right? Because suppose I give 2 or 3 hours, then you do not have time, right? Then you have to write most essential steps. But since you do not have any time constraints, take your time and write them in a clear manner. Okay. Right. Okay. Any questions? Any other questions? Right. So we would continue our discussion about Laplace transform. Okay. I would recall what we did so far. I gave the definition of the Laplace transform. So you have function ft means, and then we defined the Laplace transform in this way. It is the integral from 0 to infinity t e to the minus st dt. This is how we defined the Laplace transform. Okay. And we use this basic idea to compute Laplace transforms of basic functions. Okay. So we evaluated the Laplace transform of 1. Okay. That was 1 divided by s. Then we evaluated the Laplace transform of t to the power n. That was factorial n divided by s to the power n plus 1. Okay. Then we discussed the Laplace transform of e to the at. This is valid for s greater than 0. This is also when s is greater than 0. And the Laplace transform of e to the at is 1 divided by s minus a. And this is valid when s is greater than a. Right. Then finally, I discussed Laplace transform of cosine omega t. That was s divided by s square plus omega square, right? When s is greater than 0. Okay. Those are the things that we discussed so far. And also I discussed about the linearity. Right. Then we proved that Laplace transform is a linear transformation. That means this operator L would satisfy two conditions. Those are the Laplace transform of f plus g going to be equal to Laplace transform of f plus Laplace transform of g, and Laplace transform of c times f is equal to c times Laplace transform of f. Those are the two conditions. Okay. Right. So I proved these four things, right? And the hardest one was the Laplace transform of cosine omega t, right? So I did that in a different way from the lecture notes. Okay. So I would add another formula to this one that I'm not going to prove, but the proof is kind of same as Laplace transform of cosine omega t. That is the Laplace transform of sine omega t. That would be Laplace transform of sine omega t is equal to omega divided by square plus omega square. This is greater than 0. Okay. And also when we are taking the Laplace transform, we need only the portion of where t is greater than or equal to 0. Because by the definition, Laplace transform of some function is the integral from 0 to infinity. We are integrating time from 0 to infinity. So we do not need function to be defined at non-negative times. Okay. So it is clear from the definition, this definition, right? So we are integrating t from 0 to infinity. Okay. So we do not care about negative t's. Okay. So it would be enough that function is defined only for negative t. Okay. Function need not to be defined for negative values. Okay. All right. But function should be well defined on positive times. Okay. Right. So right now we have these 5 formulas, right? And we have the idea of linearity. Those ideas are the main facts that we discussed. Okay. Then I would like to put my focus on hyperbolic sine and hyperbolic cosine functions. First, we would evaluate the Laplace transform of hyperbolic cosine. Right? Let's evaluate the Laplace transform of hyperbolic cosine and hyperbolic sine function. Okay. What is the definition of hyperbolic cosine? Can you remember the definition of hyperbolic cosine? It would be e to the x plus e to the minus x divided by 2. Hyperbolic sine x would be e to the x minus e to the minus x divided by 2. Okay. This is the definition of hyperbolic sine and hyperbolic cosine. Okay. Right. Now, my problem is What is the Laplace transform of hyperbolic cosine of omega t? Can you give a try? Do not try to use the fundamental integral, right? Try to use the ideas that we discussed, okay? Because we know that what is the Laplace transform of e to the at? Use that idea. Find the Laplace transform of hyperbolic cosine. I would give you 3 or 4 minutes to do this. You need this formula. Laplace transform of e to the at is equal to 1 divided by s minus a. Right? This is what you need when you are solving this problem. Let's try to apply the definition of hyperbolic cosine. Did anyone get the answer? So let's insert the definition of hyperbolic cosine, right? So plus of hyperbolic cosine omega t is equal to Laplace of what is hyperbolic cosine? It is e to the x plus e to the minus x divided by 2. Now instead of x, we have omega t. So this is e to the omega t plus e to the minus omega t divided by 2. Okay, then I would use linearity, right? 1 over 2 is a constant, so I would take that out. For 2, I have Laplace of e to the omega t plus Laplace of e to the minus omega, right? I use the linearity. Okay. Now what is the Laplace of e to the omega t? Now your A is omega t. Okay. Laplace of e to the omega t is 1 divided by s minus a. Now a is omega, right? Now this is your a, right? What is the Laplace transform of e to the minus omega t? Now instead of a, you have minus omega, right? So s minus minus omega is equal to 1 divided by s plus omega. Okay. Right. So what would I get? I have 1 over 2. Laplace transform of e to the omega t is 1 divided by s minus omega. And Laplace transform of e to the minus omega t is 1 divided by s plus omega. Okay. Right. Now let's try to simplify this. I would take the common denominator. That is s minus omega times s plus omega. And on my numerator, I would get s minus omega plus s plus omega. Okay. Okay. What would I get? I would get omega to omega would be cancelled and 2s divided by 2, that is s divided by s minus omega times s plus omega. That would give me s square plus omega square. Right. Any questions about that? You just need to apply the definition of hyperbolic cosine. Right. I think I computed correctly. As transform of e to the at and minus omega s plus omega. Any questions about that? So this is the idea of how to use the linearity in a problem. Right? So let's move on. Right. Then try to compute the. This is problem number 2. Suppose we have some function ft defined in this way. If t is equal to 1, if t is in between 1 to 3 and 0, t is greater than or equal to greater than 3, right? Find the Laplace transform of this function. Okay. Oh, I did a small mistake here. Right? This should be a square minus omega square. Right? S minus omega times S plus omega. Because we know that A minus B, A plus B is equal to A square minus B square, right? Try to find the Laplace transform of this function. Now you have to apply the definition. First, try to sketch this function. The value of this function is 1 if t is in between 0 to 3, and function value is 0 if t is greater than 3. Okay. Just the definition for that integral. Just apply the definition. So we know that Laplace transform of ft equal to integral from 0 to infinity ft e to the minus st dt. Okay. Right. Now you can see that in between 0 to 3 function is 1, and in between if t is greater than 3 function is 0, right? So I would decompose this integral as a summation, right? So I would write this integral in this way: 0 to 3 ft e to the minus st dt plus 3 to infinity ft e to the minus st dt. Okay. Is that clear? I use the properties integrals. Now what would happen to the second integral? What would happen to this integral? That would disappear, right? Because if t is greater than 3, the function would be 0. So this integral is equal to 0. Okay. So I need to consider only this first integral, 0 to 3. In between 0 to 3, function is 1. Okay. 1 e to the minus st dt. So what is the integral of e to the minus st? That is e to the minus st divided by minus s from 0 to 3. Okay. Any questions about that? Okay. Now let's plug those values, right? First I would keep minus 1 over s out. Then I would plug 3, then I would get minus 3s, then I would plug 0, then I would get e to the 0. So I would get minus 1 over s multiplied by e to the minus 3s minus 1. So my answer is 1 over s 1 minus e to the minus 3s. Okay. So this is the Laplace transform of function ft. Okay. Any questions? Then my next problem is find the Laplace transform of hyperbolic sine of omega t. Can you give a try? I evaluated the Laplace transform of cosine. Now can you give a try to find the Laplace transform of hyperbolic sine? Apply the definition of hyperbolic sine. how do you find the Laplace transform of hyperbolic sine? So apply the definition. Hyperbolic sine of omega t is equal to Laplace of what is hyperbolic sine, that is exponential of e to the exponential of omega t minus e to the minus omega t divided by 2. Okay. Then use the linearity. You can take 1 over 2 out of your bracket. And by linearity, you can write this in this form. Laplace of omega t minus Laplace of e to the minus omega t. Okay. Right. Now we discussed previously what is the Laplace of omega e to the omega t. That is 1 divided by s minus omega. And this would be 1 divided by s plus omega. Right. So if we take the common denominator, we would get s plus omega minus s minus omega divided by s minus omega times s plus omega. Okay. So in your numerator, you would get 2 times omega. If you divide that by 2, you would get omega. So you would get omega divided by square minus omega square. Okay. Any questions? So right. So this is the Laplace transform of hyperbolic sine. Okay. Right. So I would again summarize what we did so far. Right. So what is the summary so far? We discussed Laplace transform of 1, that is 1 divided by s. Laplace transform of e to the at, that is 1 divided by s minus a. And Laplace transform of t to the power n, which is equal to factorial n divided by s to the power n plus 1. This is for s greater than 0. This is for s is greater than a, is greater than 0. Okay. And we discussed Laplace transform of sine omega t, which is equal to omega divided by s square plus omega square. And we discussed Laplace of cosine omega t, which is equal to s divided by square plus omega square. Then we discussed Laplace of hyperbolic cosine omega t, that is equal to s divided by square minus omega square. And finally, Laplace transform of hyperbolic sine of omega t, that is equal to omega divided by square minus omega square. Right? So I think this is greater than omega. Yes. This is valid is greater than omega because we are using this equation when we are proving, right? And we discussed linearity, right? Linearity is very important. If I give you a piecewise defined function, and if I ask you to find the Laplace transform of that function, you have to use the idea of linearity. Any questions so far about the ideas that we discussed related to Laplace transform? And also remember that t is greater than or equal to 0 because when t is non-negative, when t is negative, we cannot say this is the Laplace transform, right? Because we are always we are always integrating from 0 to infinity, right? So we are not integrating the function in non-negative t values. Okay, remember that fact also. T is greater than or equal to 0, right? Okay. Right. So I think you remember the idea of a step function, ut, that I defined in the last class. I defined ut in a way that ut is 0 if t is negative and ut is 1 if t is positive. Okay. So again, I would write down the definition because for the next idea that I'm going to discuss, we need that idea. Recall what was ut? Ut is equal to 1 if t is greater than or equal to 0, and ut is 0 if t is less than 0. Okay. Sometimes we call this function as unit step function, or sometimes we call that as a step function. In engineering, one of the important thing in control theory is how your system behaves under unit function, right? This is the function. Okay. Right. Right. So in the Laplace transform, we are interested in t positive case, right? So suppose you have some function and you need the positive part of that function. That positive part means you need the portion of the graph when t is greater than or equal to 0. So this is the idea. So suppose you have some function. Suppose you have some function like this. Okay. You would like to extract this portion, right? You need to cut off the other region, right? You need to cut off this region, right? You do not need this. How do you extract this red colored portion? How do you extract this red colored portion out of this graph? Any ideas? This is the graph of FT. This is the graph of FT. Right? How do you extract this portion? Red colored portion.
Set the limits from, I said you set the limits from 0 to. Guess
Yeah. Yeah, that's correct. But I need an expression for FT. I need an expression for this red colored portion. Total graph is FT. So what is this red colored portion? Use the definition of UT. So the whole graph is FT, right? So what this red colored region, red colored graph? What would happen if you multiply FT by UT? What would happen if you multiply FT by UT? When T is positive, UT is 1, right? 1 multiplied by FT is FT, right? But when T is negative, what is UT? 0. So the blue colored portion would disappear if you multiply this graph by UT. Is that clear? Right. So multiply this graph by UT. Multiply by UT. T is Y. So you would get this portion, right? This is FT times UT. Okay. Is that clear? Because UT is 0 when T is negative, right? So this portion would disappear because you are multiplying this portion by 0. Okay. I would give you another example. Suppose if T is equal to 2T, T can be any real number, right? So what is FT times UT? Right? FT times UT is equal to if T is 2T, 2T times 1 if T is positive, right? Because UT is 1 if T is positive, and 2T times 0, which is equal to 0 if T is negative. Okay. So UT has a good control over this function, right? That's why this UT is going to be very important. So if you sketch the function UT, FT would be a linear function and it would look like this, right? This is FT equals to T. Now we are multiplying this. Now you multiply this function by UT. Multiply by UT, right? Then what would happen? This portion would disappear. Right? This portion would disappear. This is the graph of FT times UT. Is that clear? Any questions about that idea? Because this idea is going to be very, very important in future classes, right? Right. Then my next question is this. These things are not in lecture notes, but I need you to know these things, right? Because if not, it would be difficult to understand future ideas, right? So next problem is H, the graph of if t equals ut minus 3. Try to sketch ut minus 3. Right? First, can you sketch the graph of ut minus 3? Sketch ut minus 3, right? And I'm checking right? So try to sketch ut minus 3. Ut is the standard graph. When t is positive, ut equals 1, and when t is negative, ut equals 0. Right? Use that idea to sketch ut minus 3. Going to check your answers after 2 minutes. Minus. It's ut, right?
It's a T, that's a T minus 3.
T minus 3.
Minus 3.
T from ut. Right. So how do you sketch UT? First sketch UT. We know how UT looks like. This is the graph of UT. Okay. Right. Oh. I saw most of you have sketched some graphs like this, right? That would never happen, right? Because now you are going to draw UT minus 3, right? So it should be related to UT, right? Right. So let's use fundamentals, right? So our target is to sketch UT minus 3. Okay, right. Let's substitute some values and check, right? Let's substitute 0. Right. So now our target is to sketch UT minus 3. Now what would you get if you substitute 0? What is the value of this one? What is the value of this one? U minus 3. So what is that value? 0, right? Because we know that U minus 3 is 0. This is the graph of UT. Minus 3 is somewhere here, right? U minus 3 is 0. This is 0, right? So what can you say about U1? It means it is also 0, right? That means if you plug 1 instead of 3, you get U minus 2. That is also 0. Okay. If you plug 2, you get U minus 1. Minus 1 is somewhere here. It's also 0. If you plug 3, you get U0. It is equal to 1. Right? So when you are plugging some value greater than or equal to 3, you get 1. And if you plug something less than 3, you get 0. Right? So what is the shape of UT minus 3? Right? 3 is the important point. So this is kind of horizontal translation. I think in trigonometry, you are doing that, right? You know how to sketch sin x, then sin x minus pi divided by 2. You have to translate your graph, right? By 3 units. Okay. Is that clear? Right? It's a very easy problem, right? It's UT minus 3. So what can you say about UT minus 5? Then you are taking this step at 5, right? So that would determine where you are going to take the step. Okay. Right. Then how do you sketch? I'll give you another one. How do you sketch UT plus 2? Can you sketch that one? Now minus 2 is the important point, right? Because if you substitute something greater than minus 2, suppose you are going to substitute minus 1, then you get U1, and U1 is equal to 1. Because this is a graph of UT. So at 1, you are going to get 1, right? So UT plus 2 would look like you are going to take the jump at minus 2. Okay. Right? Now we can move back into our problem. My problem was to sketch ut minus 3, right? Right. So how do you sketch this graph? First, let's figure out ut. So ut is this one, right? This is ut, right? You are taking the jump at 0, right? So what is the shape of ut minus 3? This ut. How do you sketch ut minus 3? You're taking the jump at 3. So what can you say about difference of these two graphs? What would you get? You're going to subtract the second graph from the first one. So you get only the portion from 0 to 3. Okay? Because one here, you are subtracting these two. So you get this portion, right? 0 to 3. Okay? Right. Any questions about step function? This is going to be very, very important, right? That's why I would like to do more exercises from this idea, right? Any questions? Is that idea clear? If you have any confusions, please ask. Because if you know how to understand these step functions, you can solve many problems related to Laplace transform. Okay. Okay. We would take a small break and continue. Right. 3 or 4 minute break. Okay. Right. So, are there any questions before I move into the next idea? So I would introduce the inverse Laplace transform. Inverse Laplace transform. Right. Suppose you have two functions, two positive functions. Suppose that Laplace transform of ft is going to be equal to Laplace transform of gt. T is positive. Okay. So we can we do not need to write t greater than or 0 in each step. If we can write this in this way, right? Ft ut is equal to Laplace transform of gt ut. Okay. That means we are considering t greater than or equal to 0 part. Okay. Because by multiplying ut, we are ignoring the portion of the graph where t is negative. Okay, that would become 0. So if Laplace transforms of two functions are equal, then the functions are equal when t is greater than or equal to 0. Then ft ut is equal to gt ut or ft equals gt when t is positive. Okay, same idea, right? Ft ut means we are considering ft when t is positive. So that means suppose you know we consider that Laplace transform of 1 is equal to 1 divided by s. That means inverse Laplace transform of 1 over s is 1 times ut, not 1, right? Okay, I would mention that here. Right. So that Laplace transform of 1 is equal to 1 divided by s. That means this is how I write inverse Laplace transform of 1 over s is equal to 1 times ut, which is equal to ut. Okay, ut is a step function. Okay. So here also I would write ut, then you have no confusions. T is equal to 1 over s. Okay. Then we saw that Laplace transform of t to the power n. Again, we consider t positive case, so I would multiply that by ut is equal to factorial divided by s to the power n plus 1. So inverse Laplace transform of factorial n divided by s to the power n plus 1 is going to be equal to t to the power n ut. Okay. Now we are familiarized with ut. Ut is a step function. Multiplying by ut means I'm considering the function when t is positive. Okay. Similarly, Laplace transform of cosine omega t ut is going to be equal to s divided by s square plus omega square. That means if you take the inverse Laplace transform of s divided by s square plus omega square, you would get cosine omega t ut. Okay. Same thing would be applied for each function that we evaluated, the Laplace transform. Okay. This is the idea of inverse Laplace transform. Right. So in general, suppose you have some function ft times ut, and you are taking the Laplace transform of that. Suppose you get capital Fs, right? That means if you take the inverse Laplace transform of capital Fs, you would get ft times ut. Okay. Then there's another important fact. We discussed that Laplace transform is a linear operator, right? Similarly, you can apply the same idea for inverse Laplace transform. Inverse Laplace transform is also a linear operator. Okay. Inverse Laplace transform is also a linear operator. That means if you take the inverse Laplace transform of Fs plus capital Gs, you would get and inverse Laplace transform of C times capital Fs, that is equal to C times inverse Laplace transform of capital Fs. Okay. Use the linearity and change the trace. Remember these two facts, right? Laplace transform of ut is equal to 1 over f, and Laplace transform of e to the at is equal to 1 divided by s minus a. Just the linearity, right? So first you can write our target is to find the inverse Laplace transform of capital Fs is equal to inverse Laplace transform of 1 over s plus 1 over plus 4. Okay. By linearity, I can write this in inverse Laplace of 1 over s plus inverse Laplace transform of 1 over s plus 4. Okay. So what is the inverse Laplace transform of 1 over s? Ut. Right? And what is the inverse Laplace transform of 1 over s plus 4?
E to the negative 14.
Very low. E to the minus 40. Yeah. To the minus 40 ut. Right? Because we know that from here, we know that inverse Laplace transform of 1 divided by s minus a is equal to e to the at ut. Okay. So if I plug minus 4 instead of a, I would get the inverse Laplace transform of 1 divided by s plus 4. Okay. So here, if you plug minus 4 instead of a, right, you would get s plus 4. Right. Any questions about this example? Right. So let's do another one. Consider ft equals 1 over rho s divided by s plus 1 times s plus 2. how do fs, right? Not ft. Find the inverse Laplace transform of capital F. Now you cannot use linearity, right? Now we have rational function. So what would be the first step? We don't know. We cannot directly write what is the inverse Laplace transform of this function. Right. So let's try to decompose this function by using partial fraction decomposition. I think all of you are familiar with partial fraction decomposition from calculus 2, right? So in the denominator, you have two linear factors. So how do you find the partial fraction decomposition? So s divided by s plus 1, s plus 2 is equal to a divided by s plus 1 plus b divided by s plus 2. You have to solve for capital A and capital B. Okay. So how do you solve for capital A and capital B? Take the common denominator of your right hand side. A times s plus 2 plus b times s plus 1 s plus 1 times s plus 2. Okay. Now you can have an identity by equating numerators. Okay. So by equating numerators, I have s is equal to a times s plus 2 plus capital B times s plus 1. Okay. What is the method that you can use? Heaviside method. Okay. So this is an identity. So what is the difference between identity and equation? What is the difference between identity and equation? Now this is an identity, and I'm asking what is the difference between identity and equation? Identity is valid for any value of your variable. For example, I think in trigonometry you might have come across a Pythagorean identity, right? For example, consider this one. For sin square theta plus sin square theta is equal to 1. This is an identity because this whole pi over 2, pi over 4, pi over 3, pi over 12, any value that you like. Right? So this is an identity. But if I have something like this, sin of theta is equal to 1, this is an invariant. Okay? Because this is not true for any value of theta. For example, if you put 0, this is not true. This is true for odd multiples. This is true for pi over 2. Right? This is true for 2 pi plus pi over. Right? So this is true for certain values of theta. Okay. So therefore, this is an equation. This is an identity. That is the difference between identity and equation. Okay. Identity is true for any value of your variable, but equation is true for certain values of your variable. Okay. Right. So this is an identity. So I can put any value for s, right? So there are two values that I can substitute for s and get values of a and b. What are those two values? Yeah, -1 and -2. So I would put s equal -1. Then I would get 2 times -1 is equal to a times -1 plus 2 plus b times 0. Okay. So I would get a equals -2. Right. Next, I would plug -1, -2. Right. Next, I would plug s is equal to -2. Then what would I get? 2 times -2 is equal to a times 0 plus b times -2 plus 1. So I would get -4 equals b times -1. Okay. So B would be equal to 4. Right? Now I have the values of A and B. A is equal to -2 and B is equal to 4. Right? Okay. Next, I would write down the partial fraction decomposition of my rational function. Okay. This is my rational function. So I would plug -2 instead of A and 4 instead of B. Okay. Any questions so far? Okay. Now we can evaluate the inverse Laplace transform. Okay. Right. So this is my Fs. So let's evaluate the inverse Laplace transform. Inverse Laplace transform of this big function. So S divided by S plus 1 times S plus 2 is equal to inverse Laplace transform of, I know the decomposition of this rational function. It is equal to -2 divided by S plus 1 plus 4 divided by S plus 2. Okay. Then I would use the linearity of inverse Laplace transform. Okay. So by using linearity, I can write this in -2 times inverse Laplace of 1 divided by S plus 1 plus 4 times inverse Laplace transform of 1 divided by S plus 2. Okay. Is that clear? I use the linearity. Right. Now, what is the inverse Laplace of 1 divided by S plus 1? And what is the inverse Laplace transform of 1 divided by S plus 2?
E to the negative t.
Yeah, e to the negative t and e to the negative 2t. Right. Again, recall Laplace, inverse Laplace of 1 minus 1 divided by S minus A is equal to e to the at ut. Okay. So I would get -2 e to the, now I need S plus 1. So instead of A, I need to put -1. Negative t ut plus 4 times e to the -2t t. This is my answer. Okay. Any questions? Right. I would move into another property of Laplace transform. the proposition. Suppose that A is a positive constant. Then and if T is defined for T is greater than or equal to 0. Okay. Then Laplace transform of Ft is equal to Fat. If At is equal to 1 over A times F is over A. Okay. Where capital F is the Laplace transform of simple F, right? Okay. Then I'm going to prove this. So I have a function Ft and I know that its Laplace transform is capital F. Know that Laplace transform of simple Ft is equal to capital Fs. Let's prove this. I'm using the given fact. I have some function simple F and A is a positive constant. A is greater than 0. Right? I know that Laplace transform of function Ft is equal to capital Fs. Okay. What is my target? My target is to find Laplace transform of Fat. Okay. I would apply the definition. What is the definition? This is going to be equal to 0 to infinity Fat e to the minus st dt. Okay. Right. Any questions so far? Next, I would use a substitution, right? Instead of At, I am going to insert U. Use U equals At substitution. Okay. So what would happen to your limits of integral? When t equals 0, U is 0. And when t goes to infinity, U is also infinity, right? So, right, this is equal to 0 to infinity. Fu and e to the minus s, what is t? T is u divided by a, right? And also I have du is equal to a times dt. So I need dt is 1 over a times du. Okay. Because I know that du is equal to a times dt. So dt is 1 over a times du. Okay. Then you I can take 1 over a out. So I have 0 to infinity fu e to the minus s. I would write this in this way. E to the minus is divided by A times U du. Okay. Right. Now, what is this function? We know that. What is Fs? We know that Fs is Laplace transform of simple f, right? So Fs is going to be 0 to infinity ft e to the minus st dt. Okay. So what is Fs of A? If you replace s by s over A, you would get ft e to the minus s over A times t dt. Okay. Right. Now we know that definite integral is independent of variable. So instead of t, I can insert u. Okay. So instead of t, I would write u. If u e to the minus s divided by A times u du. Okay. Now what can you say about these two functions? This I highlighted by yellow color. I would highlight this by green color. What can you say about these two functions? They're equal, right? So I can write. So this one is equal to f is divided by A. Okay. I proved that. Right? Is that clear? Because I saw that I evaluated capital F at s divided by A and I got the same result. So now I can state that Laplace transform of FAT is equal to 1 over A capital F is divided by A. I would upload the notes that I am writing here also in the blackboard, right? Because in the lecture notes, proof is around 1 line, right? So I would upload this. Okay. So any questions? Okay. So today I would stop from this point and I would continue on tomorrow.